Throughout mankind history, Mars has entranced people around the world. It became embedded in popular culture through science fiction movies, TV, and novels. Mars has indeed captured the imagination of scientists, astronomers, and the general public alike. American and European agencies began making plans to land the first humans on Mars. Two agencies stand out among the rest: SpaceX and NASA. What was once science fiction is now becoming science facts regarding the red planet. Currently, NASA's Curiosity rover is surveying the Martian landscape for any semblance of microbial life. NASA has already learned that Mars contains signature signs of dry riverbeds, where water likely once flowed in the distant past. Mars also has a large polar ice caps, which scientists say can theoretically be transformed to ultimately create an Earth-like atmosphere for future generations of space travelers. Elon Musk has already announced big plans to make history on Mars by establishing a permanent human presence prior to NASA's launch window. However, this assumes that Musk's projections are correct and SpaceX is a success. But as any astronaut will admit, space is hard. So what technologies the two agencies are working on to get us to the moon? For the sake of their mission to conquer the Martian soil, NASA and SpaceX are developing new heavy lift rockets, SpaceX's Starship and NASA's Space Launch System. The Starship rockets go through multiple stages to get into orbit by discarding spent fuel tanks while in flight. The rocket becomes lighter and therefore easier to accelerate. Once in operation, SpaceX's launch system will be comprised of two stages: the launch vehicle known as Super Heavy and the Starship. Super Heavy is powered by the Raptor rocket engine, burning a combination of liquid methane and liquid oxygen. The basic principle of a liquid fuel rocket engine is that two propellants, a fuel such as kerosene and an oxidizer such as a liquid oxygen, both are brought together in a combustion chamber and ignited. The flame produces hot gas under high pressure, which is expelled at high speed through the engine nozzle to produce thrust. The rocket will provide 15 million pounds of thrust at launch, which is approximately twice as much as the rockets of the Apollo era. On top, the launcher sits the Starship, itself powered by another 6 Raptor engines and equipped with a large mission bay of accommodation satellites, compartments for up to 100 crew, and even extra fuel tanks for refueling in space, which is critical to long-duration interplanetary human spaceflight. The Starship is designed to operate both in the vacuum of space and within the atmosphere of Earth and Mars, using small movable wings to glide to a desired landing zone. Once over the landing area, the Starship flips into vertical position and uses its onboard Raptor engines to make a powered landing. It will have sufficient thrust to lift itself off the surface of Mars or the Moon, overcoming the weaker gravity of these two worlds, and return to Earth again, making a powered soft landing. The Starship and Super Heavy are both fully reusable, and the entire system is designed to lift more than 100 tons of payload to the surface of Mars. The spacecraft is maturing rapidly. A recent test flight of the Starship prototype, the SN8, successfully demonstrated a number of the maneuvers required to make this work. Unfortunately, there was a malfunction in one of the Raptor engines, and the SN8 crashed on landing. Another test flight is expected in the next coming days. NASA's Space Launch System. The Space Launch System SLS from NASA will be taking the crown from the discontinued Saturn V as the most powerful rocket the agency has ever used. The current incarnation, SLS Block 1, stands at almost 100 meters tall. The SLS core stage, containing more than 3.3 million liters of liquid hydrogen and liquid oxygen, equivalent to 1.5 Olympic-sized swimming pools, and powered by 4 RS-25 engines, 3 of which were used on the previous space shuttle. Their main difference from the Raptors is that they burn liquid hydrogen instead of methane. The core stage of the rocket is augmented by 2 solid rocket boosters attached to its sides, providing a total combined thrust of 8.2 million pounds at launch, about 5% more than the Saturn V at launch. This will lift the spacecraft to low Earth orbit. The upper stage is intended to lift the attached payload, or the astronaut capsule out of Earth's orbit, and is a smaller liquid fuel stage powered by a single RL-10 engine used by Atlas and Delta rockets, which are smaller and lighter rockets than the RS-25. The Space Launch System will send the Orion crew capsule, which can support up to 6 members crew for 21 days to the Moon as part of the first Artemis mission, a task that NASA rockets are currently not capable of performing. It is intended to have large acrylic windows so astronauts can watch the journey. It will also have its own engine and fuel supply, as well as the secondary propulsion systems for returning to the Earth. Future space stations such as the Lunar Gateway will serve as a logistical hub, which may include refueling. The core stage and booster rockets are unlikely to be reusable, which means instead of landing, they will drop in the ocean. So there is a higher cost with the SLS system both in materials and environment. It is designed to evolve to larger stages capable of carrying crew or cargo weighing up to 120 tons, which is potentially more than Starship. The technology used in the SLS was adapted from previous missions, cutting down the research and development time. However, earlier this month, a test fire of the SLS core stage was stopped a minute into the 8-minute test due to a suspected component failure. No significant damage occurred, and the SLS program manager, John Honeycutt, stated that they won't be looking at a significant design change. The biggest challenge intimately connected with fuel is time. Missions that send spacecraft with no crew to the outer planets often travel complex trajectories around the Sun. They use what they call gravity assist maneuvers to effectively slingshot around different planets to gain enough momentum to reach their target. This saves a lot of fuel but can result in missions that can take years to reach their destinations. Clearly, this is something humans would not want to do. Both Earth and Mars have almost circular orbits in a maneuver known as the Hohmann transfer. It's the most fuel-efficient way to travel between two planets. Basically, without going into too much details, this is where a spacecraft does a single burn in an elliptical transfer orbit from one planet to the other. A Hohmann transfer between Earth and Mars takes around 259 days and is only possible approximately every 2 years due to the different orbits around the Sun of Earth and Mars. A spacecraft could reach Mars in a shorter time as SpaceX claimed 6 months, but you guessed it, it would cost more fuel to do it that way. Suppose our spacecraft and crew get to Mars, the next challenge is landing. A spacecraft entering Earth is able to use the drag generated by interaction with the atmosphere to slow down. This allows the craft to land safely on Earth's surface, but the atmosphere on Mars is about 100 times thinner than Earth's. That means less potential for drag, so it isn't possible to land safely without some kind of aid. Some missions have landed on airbags such as NASA's Pathfinder mission, while others have used thrusters. The latter once again requires more fuel. The final challenge is the return journey and getting people safely back to Earth. Apollo 11 entered Earth's atmosphere at about 4,000 km per hour, which is just below the velocity required to escape Earth's orbit. Spacecraft returning from Mars will have re-entry velocities from 47,000 to 54,000 km per hour, depending on the orbit they use to arrive at Earth. They could slow down into low orbit around Earth to around 28,800 km per hour before entering our atmosphere. But again, that will require extra fuel. We just need to make sure we don't kill the astronaut with G-forces or burn them up due to excessive heating. These are just some of the challenges facing a Mars mission, and all of the technological building blocks to achieve this are there. We just need to spend the time and the money and bring it all together. This is it for today's video. Don't forget to subscribe. See you in the next video.